What we're about to start now, starting with Chapter 5 and through the end of the school year, is I will sometimes call it the second half of calculus. So I appreciate that we took more than half of the year to do the first half. So this is not a very precise use of the word half in that sense. But what we did before, everything we needed to know about limits so that we could compute derivatives, was first half. And now we're going to talk about the second half of calculus, the second half of first year calculus. So that focus, the whole reason to invent all of that stuff that we've learned so far was that we wanted to find instantaneous velocity. How do you find velocity at an exact moment when we acknowledge that velocity is change in distance divided by change in time? But how do you compute that if you don't want the time to change? You want to have velocity at an exact instant. So we had that idea of taking the limit as the two velocity values, the two time values got closer and closer together and got so close that they were essentially zero. So here we go. We, in this first half of calculus, learned to call the slope, a function that gave us the slope of the tangent line, we call that the derivative. We find a derivative by differentiating, and so that word differentiating, that gives us the name that we sometimes use for first semester calculus, which is differential calculus. So the calculus of finding and then using derivatives. So one of the most important things that we need to remember as we move into the second half is that when we didn't know the exact slope of a curve, when we didn't have a function to differentiate, we could make an approximation of the slope by finding the slope of the secant line. So not only was it really important for us to learn how to take derivatives, it was important for us to learn how to approximate taking a derivative when we don't have enough information available. So just to finish that line there, computing the slope of the secant line, that's the same as average rate of change. So f of b minus f of a over b minus a, change in y divided by change in x. The second half of calculus, we sometimes call integral calculus. One of the first things we're going to learn, not in this section, but in the next section, is a notation that we call the definite integral. So evaluating an integral turns out to be how we're going to spend a lot of time, most of our time, in the second half of calculus. And the focus on the second half of calculus, well, the impetus for it was wanting to find the area under a curve. So we're going to learn, number one, how to find areas under curves. Number two, how to notate that with this new symbol that's called the integral. And how, surprisingly enough, how this all relates back to differential calculus, so taking derivatives. And one of the most important things that we're going to learn as we go through this process of learning how to compute area under a curve, I'm just trying to draw a parallel to the first half of calculus. It's not just going to be important to learn how to get the exact answer, it's going to be important to learn how we can make an approximation of that answer if we don't have enough information to get the exact answer. So just recall, this is a really, really, really big idea from geometry. If you have a large shape and you want to find its area, it's sufficient to chop that shape up into a bunch of smaller shapes, find those separate areas individually, and add them together. So the area of a whole is equal, W-H-O-L-E, is equal to the sum of the areas of the parts. So we're going to do something similar. That's what this section is all about. How can we use areas to approximate, how can we use smaller areas to approximate a larger area, even if we don't have enough information to get an exact answer? So just because they are some of the simplest area formulas to use, the shapes that we're going to use commonly to sort of fill in these larger areas are rectangles and trapezoids. I hope you'll consider following along in your textbook. It's page 263. So the second half of calculus was developed completely separately from what we call the first half of calculus. So we had one group of people, trying to work on this idea of how could you say the slope of a tangent line when it's supposed to be change in y over change in x, and you don't want the x to change. We had separately a group working on this question of how do you find the area under a curve? So we know how to find lots of different areas according to some formulas that you practiced in geometry, but what if we don't have, what is not a regular geometry formula that we recognize? So how can we find the area? And here's why they were interested in that question. So go back to this problem that you've been doing forever. There's a train, it's going 75 miles an hour, and between 7 a.m. and 9 a.m., how far does it get? So we know, you can pull out this formula we've used a million times, rate times time equals distance, and I can do this multiplication. I have the rate, 75 miles per hour. I have the time, between 7 a.m. and 9 a.m. is 2 hours, and I can multiply 75 miles per hour times 2 hours to get 150 miles. And notice the units even work out. That was miles per hour times hours. The hours cancel and give me my answer in miles, which is what I was expecting. That's appropriate units for distance. So that's great. We know how to do that. And if you check in your book, there's a cool picture that we definitely want to start to understand. It just so happens that if you were to make a graph of the velocity of the train, the velocity of the train doesn't change, right? It's a constant 75 miles per hour. So here's a constant 75 mile per hour function. And if you think about between 7 and 9, the computations you performed, 9 minus 7 to make 2, and then 2 times 75 to make 150, they're the same computations you would perform to find the area under this curve, that part that's shaded blue. So, here's the problem. You know a little about this problem. I've been trying to prep you a little bit for this. There is no car or bus or train or person or bumblebee or anything that really moves at a constant velocity. So how can we start to describe distance traveled in a scenario where velocity is not constant? Because when velocity is not constant, that rate times time equals distance function, it doesn't help us anymore. So the founders of calculus surmised that just the same way that when velocity was a constant, I could find the area under the velocity curve, that even if the velocity weren't constant, here's a velocity function that is not constant, it's not a horizontal line, it's not even anything I maybe have a formula for, it's still the case that the area under the velocity curve between the travel times gives distance traveled. So once these founders of calculus confirmed that the area under the velocity curve gives distance traveled, now all of a sudden they're really interested in finding these areas under curves, even curves that we maybe have a formula for, but they don't correspond to some geometric shape that we know already how to find the area of. All right, so like I say, those founders of calculus, turns out they were right. The area under a velocity curve does in fact give distance traveled. So I'm calling that important area under curves fact number 1. This whole second half of calculus is about finding areas under curves. And the most important part of that, the part that they're going to test you on, without a doubt on the AP test, area under a velocity curve gives distance traveled. That's a big if the velocity is positive. If velocity is not positive, we'll talk about what that means a little later, but if velocity is positive, area under the velocity curve gives distance traveled. Okay, so that's great. We know that. And now we have this new tool that we can use. I always could, back since 4th grade, find distance traveled when velocity was constant, because I've used that formula, right? It turns out I was finding the area of a rectangle because I had a constant velocity and I just had to pick the time limit. So that's why that was so easy. Now, I won't know a way to compute all distances traveled for all velocity functions, but if I can draw my velocity function and determine what area I'm looking for, and I recognize that area from geometry, then I can use whatever geometry I know to find the area under the curve, and I can answer this question, what is distance traveled? So here are two examples. We'll find that in both cases we'll recognize the shape under the velocity curve, and we'll be able to answer what is the total distance traveled. So if a car moves with velocity 3/5 t plus 4, that's measured in miles per minute, for time 0 to 5 minutes, how far does the car travel during that time? So to try to answer this question, I'm going to draw the velocity curve. I'm going to identify the area under the velocity curve between time 0 and time 5, and I'm going to try to see if I recognize that area and compute it. If I can compute the area, then I have the answer to the question. So 3/5 t plus 4 is linear. If I were to graph it, I'm going to start with a y-intercept of 4. I'm going to use a slope of 3/5, so I went up 1, 2, 3, and over 1, 2, 3, 4, 5. So here's my linear function. What is that? That's 5, 7. And I know here's my velocity curve. The area I'm interested in is going to be the area under the velocity curve between time t equals 0, t equals 5. Let me mark. That's the t-axis, that's the v-axis. So that's this area here, and I hope you recognize that shape. It is a trapezoid. Back in geometry, I'm sure you spent some time finding areas of trapezoids. Most of the time in geometry, when you talked about a trapezoid, you had the two parallel sides of the trapezoid were horizontal. Here we can see the two parallel sides are vertical, but we're going to find the area this is the pattern you need to think of. So the area of this trapezoid is going to be the average of the parallel sides. So the two parallel sides, this guy, that has a height of 4. This side has a height of 7. I found that from my picture. I take the average, that means add them up and divide by 2. And I'm going to multiply by the distance across the other dimension. So if those were heights, then I'm looking for a width. Now notice there were two separate heights, that's why I had to get their average. Here there should be only one obvious answer for the width. Those two parallel sides are 5 units apart. So my answer, 4 plus 7 is 11 halves times 5, 55 halves. And just notice that, like, another way to think about this is I'm adding up the areas of all these little squares. Think about what the units on those squares are. So the time units are minutes, and the velocity units are miles per minute. So I'm multiplying miles per minute times minute to get 55 halves miles. Final answer. That's the distance traveled by that car moving at 3/5 t plus 4 between time 0 and 5 minutes. Here's another problem. I have a velocity I've been given. I've been given time limits on that velocity. I know something's going to travel at square root of 16 minus t squared centimeters per second from time 0 to 4 seconds. Can I figure out how far that particle travels over that time period? If I can draw the velocity curve and I recognize it as a shape from geometry, then I'm going to just do whatever geometry I need to do to find that area. That's going to be the answer to my question. So just notice here, if I told you that, you're probably used to seeing something more like this. Yeah, if I told you x squared plus y squared equals 16, I hope you would recognize that is a circle whose center is 0, 0, and whose radius is 4. Just notice if I tried to isolate y, this is not a function. Remember, circle's not a function because it doesn't pass the vertical line test, right? If I tried to isolate the y, I'd get y is equal to the positive or negative square root of 16 minus x squared. So the positive part is the half of the circle above the x-axis, and the negative part is the half of the circle that lies below the x-axis. So what I have here is just the top half of a circle, center 0, 0, with a radius 4. So when I try to draw this, so a circle with center 0, 0 and radius 4 is going to touch the, I would say x-axis, but in this case it's going to be the t-axis at negative 4 and positive 4. This up here is going to be 0, comma 4. Right, and this is 4, 0, and that's negative 4, 0. So, between times 0 and 4, the area under the velocity curve, that's what's going to give me my answer. I'm going to imagine shading in here between 0 and 4 under the velocity curve, and I recognize that as 1/4 of a circle. So to find the area of 1/4 of a circle is 1/4 pi r squared. In this case, I know r is 4, which makes 16 pi over 4, which equals 4 pi. 4 pi centimeters.